In this video, we're going to continue our discussion of the magnetic field generated by a long, straight wire. So in a previous video, we found the direction of the magnetic field generated by a long, straight wire, and we came up with the right-hand rule. So the right-hand rule for finding the direction of the magnetic field of a long, straight wire is that if you have some current, say I1, pointing into the board, so our X indicates that the current is pointing into the board. So imagine that we have some copper wire that is moving into the board here. We stick our thumb in the direction of the wire, of course the thumb of our right hand only, thumb in the direction of the current, and our fingers curl in the direction that the magnetic field circulates around the wire. So our current moving into the board has a magnetic field circulating in the clockwise direction. We can use the same rule for our current pointing out of the board. Thumb points in the direction of the current, and our magnetic field circulates in the counterclockwise direction. Now, in this video, we are going to take this one step further, and we are going to start finding actual values and directions for these magnetic fields. Now, Biot-Savart, this is the Biot-Savart law, and it has this complicated integral in it in which you have to take the cross product of dl cross r hat. Remember that we got this idea of the circulating magnetic field from looking at the direction of this dl cross r hat term in a previous video. Now, in this video, we're not going to actually go through the steps of solving the Biot-Savart equation. Rather, we are going to magic to a solution and see if it seems at least plausible. So, if we solve the Biot-Savart equation for an infinitely long straight wire by actually taking this integral, we find that the magnitude of the magnetic field is equal to mu naught I divided by 2 pi r. Okay, well, step one, mu naught I, that looks like it could come from the Biot-Savart equation, certainly. And it makes sense that if I have more current, I should have a larger magnetic field. So it seems like I should have an I in the numerator of my magnetic field. The R in the denominator, well, if I'm further away from my wire, it seems like my magnetic field should be weaker. And that, in fact, turns out to be the case. So the equation at least logically makes sense from the point of view of values that are in the numerator and values that are in the denominator. Okay, so the next thing we can think about is, what do these values actually mean? Well, I is obviously the current flowing through our wire. R is the distance from the wire to the point of interest. So, for example, say I want to find the magnetic field here at the point I have labeled as A. R is the distance from the wire to that point A. If I was interested in some other point, so I could be interested in some other point out here, for example, and then I could have some other R associated with that point, right? Whatever point you pick, you are going to have a distance associated with that point. That is what goes into the denominator of your Biot-Savart law. Or, well, this solution of the Biot-Savart law for a long straight wire. Okay, so mu naught, well, mu naught is just mu naught, though it's helpful to actually see that this makes our units work out. Mu naught has a units of Teslas times meters divided by amps. Well, magnetic field has units of Tesla, so whatever is over here had better have units of Tesla. So the divided by amps cancels out the units from I, and the meters cancel out the meters from R in the denominator. So that is another nice double check. The units of our solution work out. Okay. And because our solution to the Biot-Savart equation here only comes as a magnitude, we still have to rely on the right-hand rule in order to give us our direction for the magnetic field. So if we look at a given point, the magnetic field is going to be tangent to the vector, a vector tangent to the circle. So the direction of the magnetic field is given by a vector tangent to the circle. So the circle, I mean the circular magnetic field at a given radius. Tangent to the circle is the vector that touches the circle at only one point, the point that I'm interested in. Now there are really two vectors that are tangent to this point. There's a vector pointing to the left or a vector pointing to the right. But we always pick the vector that corresponds to the direction of the magnetic field circling. So if we wrote down the magnetic field at point A here, well, it's mu naught I1, because this is current I1, times 2 pi r in the negative x hat direction. We didn't do any math to get that. We simply looked at our circle, which we drew by using the right-hand rule, and we said, hey, look, at the very bottom of my circle here, the tangent vector to this point points in the negative x hat direction. Therefore, the magnetic field has direction negative x hat. So our overall strategy for finding these magnetic fields is we're going to pick a point. We are going to apply our known magnitude direction, which depends only on current and radius. And then we are going to pick a direction based on where we are on the circle, just by the geometry of the picture. We're going to manually insert that direction. Okay, we could pick another point, point B here. Well, I'm on the same circle, so my radius has not changed. So my magnetic field is mu naught I1 over 2 pi r in the positive y hat direction. Why the positive y hat? Well, that is the direction of the tangent vector to the circle at that point. We have a few other examples here. If we have some current coming out of the board here, if we pick the point D, remembering that our right-hand rule says the current will circle in the counterclockwise direction here, at the point D, my magnetic field points straight down. I again have some radius r. That is, the point D is some distance from the current here, and my direction is straight down. So at point D, my magnetic field goes like mu naught I2, where I have some other current here, in the negative y hat direction. And we can do the same thing for point C. Point C clearly points in the left direction. The magnetic field at point C points to the left here. That is the direction of our tangent vector. And so we can write down the magnetic field of C as our magnitude multiplied by negative x hat. Now let's look at a more specific example of finding the magnetic field and then using that magnetic field to find the force on a charged particle. So to begin with, our setup is that we have a wire with current moving to the right. We have an electron at point P, and we are looking to find the force on the electron at point P. Now, point P is just an arbitrary point that we have chosen, and we have said that it is some distance r directly below our wire. Okay, we've been given a few different initial conditions here. So we know the radius, so we know how far our electron is from the wire. We know the current through the wire. We know the charge of the electron, and we know the electron's velocity. It is in the negative y hat. The electron is moving downward. Now, we didn't have to specify the location of the electron along the x-axis because the magnetic field is constant everywhere on the same distance below the wire. So as long as I am a distance of 2.02 meters or 2 centimeters below the wire, I have exactly the same electric field here as here, for example. This comes from the fact that if I look at my magnetic field, it depends only on my distance from the wire, and I get the direction from looking at the right-hand rule. But when I do the right-hand rule directly below the wire in this case, I always get a magnetic field into the board. Thumb points in the direction of the field, my fingers curl in the direction into the board below the wire. So I know that everywhere below the wire, when I'm directly below the wire, the magnetic field points straight into the board. Okay, so let's review our strategy for solving this problem. First, we're going to use the right-hand rule to find the direction of the magnetic field circulating around the wire. Well, we've already done that. We stick our thumb in the direction of the current. Our right hand curls out of the board above the wire and into the board below the wire. Next, we're going to use our magnitude of the magnetic field for a long straight wire to calculate the magnitude of B. Putting these two things together, so our third step is we combine the magnitude and the direction from steps 1 and 2. And this looks like this equation here. We have our magnitude, all of these values are positive, multiplied by the direction into the board is the negative z hat direction. We're using our standard coordinate system where the positive x direction is to the right, the positive y direction is up out of the board, straight up, and the z direction is out of the board. So this is what our magnetic field vector looks like. It is the combination of our direction from using the right-hand rule and our magnitude from using our equation. Okay, plugging in these values, we get a magnetic field into the board with this magnitude. So now our final step is simply to calculate the force using our Lorentz force equation, our magnetic force equation, F equals QV cross B. So here we have it. We have our force, the charge, multiplied by the cross product of the velocity and the magnetic field. Now, we could formally take the cross product by doing the determinant, but in this case, it's actually quite easy if we remember that the cross product of two perpendicular vectors, the magnitude of that cross product, so the magnitude of V cross B is equal to VB sine theta, where this is the magnitude of V and the magnitude of B. I've signified that by not writing a vector symbol above them, multiplied by the sine of theta. But since the velocity and the magnetic field, one is down and one is into the board, make a 90-degree angle with one another, the sine of 90 degrees is just 1. And so our magnitude of magnetic field is simply the product of V and B. So this gets us the magnitude, and then we can just use the right-hand rule to find the direction. So here we're going to use our right-hand rule for the force. That is, index finger points in the direction of the velocity, other fingers point in the direction of the magnetic field, and our thumb points in the direction of the force. So we have V downwards, we have the magnetic field into the board, which puts my thumb, and therefore the force, to the right. Now, because our charge is negative, we end up flipping the direction of that force, so we pick up a minus x hat as our direction. So just to quickly review that again, we did a little bit of a shortcut in calculating our cross product. We took V cross B, and we used the shortcut that the cross product is equal to, or the magnitude of the cross product is equal to the product of the magnitudes of the individual vectors, the velocity vector and the magnetic field vector, multiplied by the sine of the angle between them. Because that angle was 90 degrees, that sine of theta is 1, and our magnitude is simply the magnitude of V multiplied by the magnitude of B. We then use the right-hand rule to get our direction, which was to the right. And then we multiplied by the negative charge, which flipped the direction of our force to be the negative x hat direction. So our final force on our particle is negative 4.8 times 10 to the negative 22 newtons in the negative x hat direction. As a final example, let's look at the force between two wires carrying current. So the basic idea is that I have two wires, both carrying current out of the board, and I'm specifically looking for the force on my second current, which I call I2, due to the first current. Now, it makes sense that these two currents should provide a force on one another because, well, they're each generating a magnetic field and they are each carrying a current. Therefore, I1 creates a magnetic field at the location of I2. I2 then feels a force given by our force equation IL cross B, where here, if I'm considering, say, the force on particle 2, or on current 2 rather, then I'm looking at the current in my second wire, I2, the length of my second wire, L2, and the magnetic field generated by the first wire, which I would call B1. So I have that written out here. So the first two terms are associated with the wire that is experiencing the force. I associated with the wire experiencing the force. L associated with the wire experiencing the force. The last term here, the magnetic field, that is the magnetic field that the wire is immersed in. Well, the magnetic field that I2 is immersed in is the field generated by I1, which I have drawn here. Okay. So our basic setup is going to be exactly the same as when we were looking for the force on the electron in the previous example. So we're first going to find the direction of the magnetic field due to I1 using our right-hand rule. So the current is coming out of the board, the magnetic field is curling upwards in a counterclockwise direction. Specifically at the location of I2, the tangent to this circle points straight up, so my magnetic field points in the positive y direction. Next, we use our magnetic field magnitude equation for a long straight wire, mu naught I over 2 pi r, and then we combine the direction and magnitude to get our total magnetic field at the location of interest as a vector. So that is mu naught times I divided by 2 pi d, where d is the distance between the wires. It's taking the place of our r in this case. This comes from my magnitude equation. Notice I'm using I1 here because I care about the current creating this magnetic field, I1. And it points in the positive y hat direction because I know that the magnetic field is circulating in this way. Okay, and then our final step is we calculate the force on I2. So we take I2, the current being acted on, multiply by its length, L2, and then we take the cross product of L, and remember that our L vector has units of length, so it is how long is this wire, for example, 2 meters, and it has direction in the same direction as the current. So in this case, I2 is coming out of the board. That is our positive z hat direction again, which means that L2 is some length L2, whatever the length of our wire is, in the positive z hat direction. We cross this length with our magnetic field, and we're going to use the same trick again where we just realize that the magnetic field pointing straight up and the current coming straight out of the board are at a 90-degree angle, and therefore the cross product, the magnitude of the cross product, is simply the product of our length and our magnetic field. And we can use the right-hand rule to figure out the direction, which is just I, B, and so the force moves to the left. That is, my first finger points in the direction of the current, my other fingers point up in the direction of the magnetic field, and my force points to the left. So, using the right-hand rule to find the direction of this cross product and our shortcut to find the magnitude, we end up with a force of mu naught times I1, which came from our magnetic field equation, times I2, which came from our force equation, times L2 divided by 2 pi d. And this points in the negative x hat direction and has units of newtons. Now, if we wanted to actually calculate a force, obviously we would need values for all of these things, including the length of the wire. So we would have to pick some length of this wire, say 2 meters of wire, and we could find the force on that 2 meters of wire.